Great. Hopefully you can hear me now online. We're going to share sound. There. Great. Okay. Today we're finally going to jump into patterns, something we've been wanting to do for quite some time, I know. We need to have a conversation about attendance in class, but I will save that for an email. So there's patterns are the way that we do traditional quote unquote type music composition in Superflighter. They can be really powerful for a number of applications on that front. But the first is that we can compose complex pieces that are fixed in time and will always be very predictable about the outcomes of what we expect with respect to tonality, individual notes, timing, rhythm, etc. Patterns can also be really useful in the composition of algorithmic works, which rely upon probabilities or other algorithms, for lack of a better word, to drive work, in which case there would be an emergent quality to the work, and it's always going to be a little bit different every time you listen to it. And that can be as simple as just having a couple random elements in a pattern so that they always change back and forth, so to speak, random. The last thing that patterns can be useful is for actually in live coding situations in which you'd sit down with a blank screen and want to build up a piece in real time in response to the energies and happenings of that space. And we'll get more into that later, but it's something to be aware of as well. I've updated the README on the main GitHub, and there's a couple of links for places to get some additional information. There's a practical guide to patterns, SC documentation, which we'll kind of work through today actually as our base. And then also this in a gentle introduction to Superflighter, part 2 has a lot of great information on patterns. It can be a really useful place also as you're working through things. So just something to be aware of. Great. Go back. So I've got this, we'll pull this up to the new page. So here we go, basic pattern guide. And then we've got some pattern cookbooks, which is also nice. So let's start with here, this basic vocabulary. Pbind stands for pattern binding and essentially creates event lists that Superflighter works through. So an event list is no different than when we were creating using the .fork method, using the task or routine methods. Those also create event lists. Pbinds are just a little bit more elegant way of doing the same thing. And you can see right here, within Pbinds, we have different ways of creating lists of keys or events. There's some terminology and some ideas we should get comfortable with. This idea of primary patterns, P sequence, which will play through the entire list, repeating number of times. Prand, which creates random lists. Pxrand chooses randomly but never repeat the same item twice in immediate succession. Shuffle the list in random order and use the same random order, repeating the number of times. Pwrand, which allows for weighted probabilities. P-series, which is arithmetic series. We've got geometric series. Random numbers with equal distribution, white noise. Random numbers with exponential distribution. Brownian motion. A P function, which allows us to start doing some really cool. The function allows us to bring in additional Superflighter functionality, essentially, which can be really useful. And then Prout. And then different ways of actually working through lists of patterns, more random number generator lists. There's a whole lot going on here. Good morning.
Morning.
And so I would encourage you to actually slowly read through all of this in time. This is just trying to go through basics of it. We'll come back to that. But what we want to get to first is Pbind. And again, Pbind essentially is a pattern binding and creates these kind of key value pairs. So we're just going to I'm going to pull up actually some different code here. Get into it. So we've got a basic synth here, sine tone, and notice the arguments that we have listed for this synth. We've got our out bus. Again, where are we actually sending audio out? And this can be, as we've learned in the last 2 weeks, a physical hardware output or an internal bus that goes to another synth. We've got a frequency argument, an amplitude argument, essentially how loud is the synth when it plays, position, which is really pan position, attack, how aggressive or how quick is the attack, sustain level, and release time. And then for our variables, signal and envelope. So this is a very standard type of synth, the type that we've been creating essentially over and over and over again. And I'm going to realize I need to, I think I've set some things up wrong. So I'm going to close this, change to my other session. Close those out. Reboot super collider. Make our life easier. Wonderful. Okay. So now if we add this synth to our server, you see it gets added, and if we listen back to it, great, super exciting. All right. So in this case, we're creating a really simple Pbind. A Pbind is simply a set of comma separated key value pairs. We'll talk about that in just a second. When you use the .play method on a Pbind, you create a new object, an event stream player. This is an object you can create like an audio file player. You can pause, start, stop, and resume pattern as it plays. So notice here we're creating an environment variable, event player, assigning it a Pbind, and we're applying the method .play to this Pbind at the end. And this key value pair syntax that we're talking about, right here, the first thing is the key. In this case, we're saying instrument. What instrument are we going to use? And the value is sine tone. Notice that's the synth that we just defined and added up above. Yeah, so let's open up help on Pbinds. Great question, Matthew. Within Pbinds, there are expected key value pairs. I'm trying to remember where the let me see here. Here we go. So here are the default key values that a Pbind can expect. Instrument, and that is always going to call the synth def to be played. Is that too small? Let's make that. Yeah. And it's no different really than saying my task and we'd say and sine tone 1.0 dot two. Whoa. So in this case, when we've handwritten our task, we've just explicitly said, I want to play synth once every second. In a pattern, we use the key instrument to call that synth that we're specifying. So it's just a little bit different syntax than we've been used to.
Where are we going to call back into the pod?
What do you mean?
So you have to move
Yep, and that's sine tone.
but the sign tone is different than
Sine tone is the instrument we're playing.
okay.
So this is key. Value. What instrument? Okay, synth def. Pattern use. Does that make sense?
And maybe there is, maybe I'm conflating a little bit important, but in my case, I just don't understand what the background is.
It's telling the pattern what synth def to use. So let's say we had a different synth def. That actually was white noise bursts. We don't care about any of this. We'll call it white. And we'll get here in just a second, okay? So know that we now have another synth def called white bursts that we've added in. Okay, event player gets Pbind. We're saying in Pbind that we're going to assign an instrument. That instrument is going to be a sine tone synth def, and that the interval between onsets is going to be half a second. And then we're going to play that event player. So if I hit execute or compile. Okay. Now if I say white bursts.
Where I get the sign tone white burst. I just don't understand the instrument. And we can name that.
Instrument, no, this won't.
But we can name for example,
This is telling, this is essentially like passing in an argument. You know how sometimes we'll go like sign os.ar, and then I'll explicitly write in the argument that we're going to pass in. I'll identify it as free. We'll say 200 hertz. This is the same thing. This is saying what value, what for the argument instrument, what are we going to call?
okay.
Again, without instruments, we get an error because it doesn't know what the heck we're trying to do. No. So notice now if I try to call white bursts, not calling it. Why not? Because instrument is the named property that we're trying to assign for a pattern.
Oh, okay.
So this pattern is saying, what instrument do you want me to use? You want me to use white burst or sine tone.
Okay.
If I try to tell this pattern, what instrument do you want to use for instrument two? It's like, I don't know what instrument two means. It's like an
You
argument.
always messing up with the backslash when you feel as if it was something that you could.
This is how these key value pairs work in a Pbinds. It just creates a symbol. Just creates a symbol.
Yeah. In my mind, I was seeing the backslash as away from me, not as something. Okay, so
I
instrument
think-
is part of Pbinds.
And I don't know if there's any other syntax we can use for that. So let's see here if they've got anything else written.
Yeah, so that was what we-
I think we actually can. So I think if it bothers you to see it written that way,
it doesn't necessarily bother me.
let's see. I think, well, let's see if this throws an error or not.
Yeah, that's
Yeah, it doesn't like that. So it's got to be written using this symbol notation.
okay.
And it's just, again, a list of always two values, the key that we're assigning, and then the value for that key.
So I don't want to go. Sorry, what exactly does that slash key of the
Mhm. So everyone's okay with this is a string, right? If we have something between double quotes or single quotes, this is right. A symbol. So we could create a synthdef that has a string as its name. A symbol, however, is prepended by a backslash and is simply a single word that can be used to reference something within the superglider environment.
kind of like,
Could be an argument, yeah. Could be a synthdef name.
okay, so it's kind of like,
It's almost like a variable. It's like a loose form of a variable.
it's like a variable, but you can call it anyway. You
You
don't
can-
have to use anything global.
Well, no, it's not global. It's just a named space, but it doesn't, it assumes that there's no spaces.
So up in line 5, for example, does that have to have
It does, I don't think we can pass it in as a string. Oh, it did. No, it didn't. It freaked out. Oh, here. So, and let's see if we can pass in white bursts.
Okay, I just have that in mind. Specifically the backslash is only.
No, and so actually, it looks like a symbol and a string can be equivalent. So if we said single word, I'm really curious here. False. Cool. Yeah. So they're different. They're different. One is a symbol, one is a string, but they can be used synonymously in certain places, which probably creates even further confusion.
Yeah, that's what I was. So what is some of the uses of
To define synths and call synths to identify values and patterns, to identify other named elements within the supercluster language.
I think that will.
Um, mhm. Cool. Okay.
Can you find that to people?
No, it's used for named entities. So it's not a, yes, we will show midterms today. For Fletcher and, who was the other person? I know there's one other, we'll figure it out. We'll do those later. Okay. So no, you can't assign a symbol. I don't believe you can assign a symbol of value. It doesn't know what that means. So a symbol is used for namespaces internally within superglider. Yes. Oh. So again, so that's key value pairs. And we'll see more about those here in a little bit. Right? If we change the duration to 1.0, we change duration to 0.5. Most sympathetic pair here is pause player. We can resume it and stop it. And then I don't know after we've stopped it if we can actually start it again.
Plus bar is the same as the synth step.
Sign it into a task.
Right?
We'll put it into a task.
Okay, yeah. And then pause it. This is just
Yeah, this is just streamlining all of that. So again, now, same thing, key value pairs, instrument sine tone, that's the instrument. Set the amplitude to be 0.2, set the frequency to be 300, and the duration to be 0.5. Right? Haven't done anything crazy, just have called up a new player. And so let's do this here. This is from another class, actually, out at Wellesley. I was just borrowing their code. We'll go through and do this. Okay. Amplitude 0.2, frequency 300. That makes sense, right? So duration, if we want that to be 0.25, we set duration 0.25. Notice for our synth def, keys can be defaulted to certain elements within the pattern that automatically are kind of set aside, such as instrument, out, gate, sustain, etc. They also can follow the argument list of the pattern itself, or of the synth itself. So in this case, we have a position element. So we'll go position, we'll go all the way out at the left speaker. We'll change our attack. These are, so there's two places that we can use these. One is either what's built in to Pbind, and if you look at the Pbind help file, you'll see that information. The other thing is that we can use key value pairs to directly address arguments of our synth defs. So in this case, we've addressed position. We're going to address attack.
Oh,
Yeah.
okay. So this isn't stuff like this.
Exactly.
So is there any way that we can listen to it? What you're
Say that again.
if we were to, okay, let's take 140.
They're the same. Ultimately, the Pbind is addressing the synth.
What if you were to, do you have an amplitude argument in your attack? That's also built into Pbinds?
There are suggested values that we would keep the same in our synths that will make our use of Pbinds easier.
If you didn't have it.
So notice they like the term pan. However, this person has used the argument position. So let's just see, sometimes these will block right up. This one doesn't, right? So if I put pan in, our synth def defines position as an argument, not pan. So I actually have to use position. I'm only on the list.
What is this? Why is your Pbinds you put an instance together or something?
Just wait. Just wait. Just wait. Yeah.
I do have a question in terms of if we had no Amplitude argument with one class, would it still like the Amplitude?
No. So like if we took this out.
Yeah.
And we'll just make it a variable that's set.
You're doing like this.
Oh, so now we go.
So all that those are doing is there's nothing built.
There are suggested keys that should be mirrored in your synth def.
We have to use it.
They don't have to be, but it's suggested. One of the things that is cool, this should work here. Let's see. If you use freak in your synth def, I believe you can use note 60. Let's see if that's right. Ooh. That's higher than middle C. Yeah. So it's pitch. Nope, it's not. Oh, but also. Yeah. Oh, and you see, so there's some hints. We're going to get to this in a little bit, but at any rate, we'll let it get us there in a second. Okay. So again, sustain. We're going to create a really style type vibe. We could create a really Licato type vibe. So again, nothing crazy. It just allows us to quickly address some of these parameters. Okay, so Pbinds generate events at intervals specified by the duration key. What exactly is an event, though? An event is simply a dictionary of key value pairs. So this is an event. We see it created an event when we created this dictionary of key value pairs. And in this case, everyone familiar with what a dictionary is? Cole, probably not, but a dictionary in computer science terminology is just another way of storing data. In SuperClatter, we can create a dictionary with the parenthesis syntax, and then it's simply a set of keys and values. In this case, instrument, sine tone, comma, amp, 0.2. So I believe I can actually call, if I remember right, I can go, right, let me see here. So I can call up those values by placing the key as an argument to my dictionary. Yeah. Right?
Yeah.
It's cool. Just get over it. It's just how the language works. We can also play that dictionary. Again, there is a default that we can play. We'll ignore that. So read through this. I think this is important. Last thing to get to is this idea of trace here. And trace simply prints the dictionary event for each event. It can be useful in debugging. We can also call specific values and only print them out. Okay. So again, a Pbind is just a binding of a pattern, and a pattern in this case is a series of events that have been compiled together. Each event is a dictionary of key value pairs that represent something that we're going to play on the server. It can be,
So
not inherently.
once you get to the end of the code,
In this case, it is, right? We're hearing that it's playing it constantly because we haven't told it not to do that.
okay, but, so I guess from a baseline perspective, it will typically be within
Well, we're about to get into that right now with P sequence. Yeah. So a P sequence creates a sequence of values that can be streamed into a pattern. So we stored P in our variable P. We converted that to a stream and I hit next once. So we got back the value 100. I'm going to hit next again and we get the value 200. Let's pull up help here on PSeq. Sequentially embed values in a list. The arguments are list, repeats, and offset. Notice we have a list here. It's an array of 2 numbers, and then it says repeat twice. We've hit stream twice. We've gotten 100, 200. When I hit stream next again, what value do you expect to get back? 100, then 200. And what will get next? What will come back next when I hit stream one again?
Oh, wait.
Because we told it to do it twice. So we got 100, 200, 100, 200. It's like, okay, I'm out of information, bro. Make sense? We could, of course, if we tell it to do it 10 times, it pulls it up for us 100, 200, 100, 200, and then the other 6 are nil again because we had nothing else in there. We can use the shorthand INF for infinite in order to tell it to repeat forever. Okay, PSeq or any pattern for that matter can be used as a value within Pbind. When Pbind generates the next event, the next value in an embedded pattern is pulled and added as the value for the key. Here are the first 9 events generated from the pattern below. So notice we're calling instrument, sine, tone, sustain, 0.05, duration, 5/10, attack, 1/100th, amp, 2/10, frequency, 400. And what we're seeing change is these frequency values, 400, 800, 600, 400, 800, 600, 400, 800, 600, 400. So we have, oh, and also our duration values. So we've created a Pbind. We're calling instrument sine tone. Amp is set at the same value. Attack is 1/100th of a second. Sustain is 5/100ths of a second. And we're going to work through 3 frequencies and 3 different durations for those frequencies. So let's just take a listen and then we can talk about it if there's anything that's unclear. Yes. So that's a very simple example, but you can start to see immediately how you could build up more complex pieces. Okay, we'll start at the right. Bearcat. No. So the pattern is doom. It's just that we play 400, we wait half a second, we play 800, wait 1/10 of a second, 600, wait 1/10 of a second, repeat 400, wait half a second. So it's doom. If you play that in succession, yeah, then you would start to get some mismatches. So again, we called trace, and let's just look through this for a little bit here. So we got instrument sine tone sustain, 5/100ths of a second, duration 0.5, attack and frequency 400. So the 2 big things here are duration and frequency. On the next one, we have a duration of 1/100th of a second and a frequency of 800. A duration of 1/100th of a second and a frequency of 600. a duration of 1/100th of a second, and a frequency of 400, which is our first value in our frequency list. Because one of these is 4 elements long and the other is a length of 3, we're offsetting them as we move through the pattern. Cool. Yes, sine time. We defined the synth up above. We added it in and we've said, let's use it. We could do the same thing with white burst. Of course, there won't be any frequency element with white burst, but we can hear the duration elements. Oh, so this is, yeah. Same thing.
So if two sequence is how do you define
Pbind creates a list of events with each event being a dictionary. The dictionary contains the synth that it wants to play and all information it needs to play that synth. Psequence just simply creates, passes in values as it's called sequentially. So when Pbinds says, hey, PC, give me your first value, it says, great, here's 400. And then Pbinds says, hey, what's your next value? Pseq says 800. And then Pbinds says, hey, what's your next value? Pseq says 600. And then Pbinds says, hey, what's your next value? Pseq says 500. Then Pbinds says, hey, what's your next value? Pseq says, oh, I'm out of values. I'm allowed to repeat infinitely. So I'll start over. My next value is 400.
so Pbinds is that Pbinds doesn't work for
No, remember, let's go back to Safari. So remember, there were all of these patterns that we can pass in to a Pbind. One of them is a P function. So we can actually pass in a function or a function that can repeat. So we can start to do other types of things using Pbinds. There's a whole lot of these things here that you have to learn. Yeah. Yeah. Cool. Cool, cool. Other questions? Cole, you had a question. Great. Anyone on the left side of the class? Right side of the class, however we view things. Cool. Okay. So once a value and a key value pair is nil, Pbind will automatically stop the pattern. For example, below, the pattern for freak will generate 4 numbers and then generate nil. Therefore, only 4 events will be created. So let's pass a trace here. Then player's done. Stream has ended, true. So let's up here play this one. Notice stream has ended is false when I hit dump and it was in the middle of playing. Here, when I dump, stream has ended is true. You don't need to know the dump stuff and all of these sub arguments, but it's just a way of recognizing and verifying that when we run out of sequence, Pbind automatically stops. So we don't have to do anything. It eloquently frees itself. There are no errors. There are no problems. because frequency only repeated once. So only could hand in 4 values, 4 frequency values, and then pseq was like, oh, I can't do any more, man. You got to be done. Cool. Interesting. We can also pass in rests. So in this example, the duration is always 0.1, and we'll call the rest class in place of a frequency. So the effect is, at the end of this sequence, essentially, we have a duration of 0.2, but you could understand how we may want to use rests in more eloquent ways as we build things up. I don't think it takes any argument, so let's see here. Because it's still a class. Value. So the rest instance is numeric value to be used in math operations. Note that a rest value is ignored in most event keys. If a rest appears in a rhythm, key, duration, or delta, then the number is the time until the next event. Cool. So yeah, in the next example, then we see that we have a rest of 0.5. No, why not? So take a listen. Why do they sound different? B, A. On the rest, we're actually resting. So we go 400, 800, rest on 400, 800, 400, rest on 800, 400, 800, rest on 400, 800, 400, rest on 800, 400, 800. So the rest is getting applied to the next value in our string. Cole, ask me the question. It's a rest of half a second length. So notice 400, 800, rest on 400, 800, 400, rest on 800. If we change the rest value, right? So it's just time-based. Exactly. That's exactly it. Say again. We're not based on seconds here either. We're based on the clock, assuming 60 beats per minute. So half a second or 0.5 beats is equivalent to a half note. Time signature is actually set up essentially through your use of duration. However, system clock.default, tempo clock. Tempo clock. I always forget. Tempo. That's then we can change our. Well, we're essentially saying how long is a beat compared to a second. Rather, how much time does a single beat take? So if we wrote 1, a single beat takes 1 second. If we wrote 2, a single beat takes no, a single beat then takes half a second. I like to do it always over 60. Yeah. That's exactly right, Bear. At any rate, get that out of there. Just know that this is based on tempo. Okay, so we can add randomness. One way to add randomness is with Pwhite. Pwhite generates random values between some lower value and upper value. If arguments are integers, then the random value is an integer. If the arguments are floats, then the random value is a float. So if we execute this, we turn it into a stream, and then we execute it a whole bunch of times. We only had 3 repeats. If we do int though, it turns a pattern into a stream of events. Typically, you don't have to think about this if you're just using it directly in a Pbind. It does that for you automatically. So in this example, notice here we have Pwhite on amplitude of 0.1 to 0.2, and we're going to make it actually quite a bit louder just so we can exaggerate that. Our sustain time is also 0.1 to 0.5. Our sequence is that same 4-note sequence repeated infinitely, and our duration sequence is 511 repeated infinitely. Pwhite can be used to generate random values between some lower value and upper value. If arguments are integers, then the random value is an integer. If the arguments are floats, then the random value is a float. In this example, we create a sequence with Pwhite. We turn that sequence into a stream, and then we'll execute it a whole bunch and see that we get values between 0.0 and 1.0. We're going to ignore this. We're going to ignore this. Okay. Oh, so it is MIDI note. Thank you, Cole. Let's execute this. So notice we're playing our same instrument, sine tone. We're passing in random values for amplitude. We have an attack of 1/100th of a second. We're passing in random values for sustain. We're working through a sequence that we have in for durations. But we're not calling frequency anymore. We're calling MIDI note. Is MIDI note part of the definition for this stuff? So this is where I talked about where if you use certain argument known names, patterns will allow us to change use use other keys that are equivalent. In this case, because we labeled our argument for frequency freak, we can use MIDI notes. And it knows to essentially turn these from MIDI note values to frequency notes. So if I apply the argument MIDI CPS, which converts MIDI CPS converts a MIDI note to cycles per second or frequency in hertz, we can see that 60 is equivalent to 261.62, etc. hertz. 65 is equivalent to 349.22 hertz. 63 is equivalent to 311. 62 is equivalent to 293. So we can start to use some of the ease of the MIDI protocol if we want to within patterns.
So would that be the same? Would that be the same?
It should. And there's some reasons why this is going to be beneficial later on. So notice here, we called trace on frequency, and it's turning our MIDI notes actually into a frequency when it passes them in. And that's what we're seeing printed out here. If we called trace on it all, we get the MIDI notes. But there are specific, because that conversion is happening, we can call trace on freak. And notice this printed function value. So it's saying, I recognize I need to do something with it. Yeah. If you play 60 on a MIDI instrument of any sort, at some level, that MIDI instrument knows it needs to turn that value, or it needs to play a value of 261 hertz. In patterns, we defined it for our synth depth. So, and this is where you were still walking into class when we went through this Bearcat, but our synth def here has arguments that are out bus, freak. You've noticed freak is a keyword that gets used very commonly, frequently around supervisor. Amp, position, this really should be pan, not position. Attack, ATK, sustain, SUS, and release, REL. Some of these ones that are common, we want to always stick with the common keyword because it's going to actually tie in, especially when we get to patterns, to make some of this a little easier. Because I needed to change it in both places. Well, I could call, if I did freak with 2 Qs and then I did MIDI CPS. But we lose all the benefit of having this shared terminology.
Yeah.
Again, you're going to be as specific as you want. And so if you need to be specific, be specific. It's just whatever makes sense. So now they're mentioning, and this is true, it turns out that there is a complex web of keys that work together to produce the frequency. So let's look at this events. We actually want to go all the way down here. Um, well, so we can look at this graph, I think is probably the most useful. So there's things we can use. We can actually define degree, scale, and transpose, and that will get translated to note, root, octave, which gets translated to MIDI notes, which gets translated into frequency. So as long as we have as an argument for a synth depth, we can start to think of our pieces in different forms. Specifically, we can kind of think in degrees and scales if we want to. Degrees of the notes of a scale. So if we have a standard major scale, degree 0, if we're assuming C major is C. It converts that into frequencies. Rather, we're not going frequencies to degrees. It allows us, depending on how we want to be doing our algorithmic compositions.
So you could start writing both. I mean, like,
Yes. Yeah. So yeah, we're going to get into some of this now. So, and then they mentioned for all this to run correctly, you need to ensure that your synth def has the argument free. In general, it's best to work at one level. Think about your notes in either frequency, MIDI note, or scale degrees, but don't mix and match. That is very true. That will usually lead to some unexpected outcomes as each level is derived from the values of the previous level. Notice, for example, how the key freak comes from the key MIDI notes. And let's see what they have for this pitch hierarchy. Okay, same thing. Discussion of clocks here that we were already having, so that shouldn't be surprise to anyone. Quantization. This is useful. So what is quantization? Say again, speak louder. Yeah, and what's the general definition of the term quantization? Because it shows up in a number of places in digital audio and music land. So this is important. Quantization is the process of constraining an input from a continuous or otherwise large set of values to a discrete set. So in digital audio, we talk about quantization in terms of bit depth. If we have a system that can record in 16 bits, 8 bits, 24 bits, etc., that's the number of values we can represent amplitude in, essentially, for digital signal. That is different from the real world in which we can represent an infinite number of continuous values. In music land, when we're talking about rhythm, quantization says, okay, we can represent the start of a note from one point to another in the real world at any moment. However, it could be useful in music land to reduce the options of possible values to a discrete set. If we're in standard 4-4 time, we might have that be 4 possibilities, split up equally across a bar. That means that when we hit go on a note, rather than be played at any point in time, it will be played at the next possible quantized value. Does that kind of make sense when I spout it that way? Everyone else feeling okay about that? Roy, feeling okay? Cool. This is useful for Pbinds because it essentially allows us to specify when to start a Pbind. So in this case, quantization is useful when we need multiple patterns to align. Execute the cells below at your own leisure. The quantization will each pattern to align to a measure. You may hear some delay between the time you execute the pattern and when you hear it. The pattern needs to wait for the beginning of the next measure. So if I hit enter now, it waited until we got to the next measure according to the tempo clock of the system. Quantization 4. There are 4 beats in a measure, so wait till the first thing. So wait till something is divisible by 4. Tempo clock we defined up above. So 120 BPM. So this is gonna make it actually go quicker. Oh. It says BPM over 60. BPM is set to 120. So clock.tempo returns. So if we did clock.tempo times 60, we see we get back a BPM of 120. No, it automatically assigns system clock. And so if this is nil, so let's pull it play on PDEF on pattern. Tempo clock that will run the pattern. If omitted, tempo clock.default is used. And we had already defined tempo clock.default. Tempo clock.default is defined the minute you start the end. Yeah, like if we just have this. Yeah, and now, yeah, if you want to use a different tempo clock. So let's say, for example, I go tempo clock default tempo equals 30 divided by 60. Good. So, whoa. We're going to back out of all this. So we're going to pass in, what do they call this one? Clock. Right? So we're passing in the tempo clock that is this new clock they defined up here. Tempo clock of 120 over 60. Again, so where was I? Here. Oh, okay. So we have this one. Say again. tempo clock.default is the default clock. So they have we want to have one clock always running. Automatically create teams, tasks, or Pbinds, some sort of default clock they can assign themselves. In this case, we've created a separate tempo clock by actually instantiating a new tempo clock instance, assigning it to the environment variable clock. And now we can change the tempos of both of these. So we can change our default back to 60/60. We can go 120/60. So listen. And we can change our clock.tempo to 120/60. Would you type? Like this. So we need to actually assign the instance of tempo clock default if we want to do that. Clock.default is now equal to T1. Tempo clock. Now we can actually change tempo clock tempo equal to 10 divided by 120. And do the same thing here. Now everything's real slow.
Sure. What if I want? Why? I just say clock variable clock one equals clock.
So we can either pass in the BPM as an argument when we instantiate a new tempo clock, or we have to actually specify tempo equal to. But what we can't do is say clock is going to equal tempo clock equal 120/60. That doesn't. Because it doesn't know that it's trying to create a new instance of tempo clock, and then we would need to specify that the tempo argument of our new instance is equal to 120/60. Because when we're working in an object-oriented programming language, when we create an instance of something, we can only set values for that instance in various ways. Okay, I'm going to do away with all of this gibberish I wrote. And we're going to keep this with clock. And we're going to reset clock to be equal to 120. Now, here's where things get more interesting. So we'll execute this first thing. We'll execute this next thing. It's a pattern of 3 notes, all 0.25 seconds away from each other. And now we've got a pattern of 5 notes with the rest in the middle being unit. You can stop them individually. You can start them individually. But if I call play without quant, it starts immediately. So same thing, event player 2, if we just call play, we would actually need to pass in that quant 4.
for your computer. Also, out of curiosity, can you name it? What would you call something that's that like variable?
It's an environment variable.
Variable? Can you make an environment variable with
Because we're pretending with a tilde, I think we can. Should you? No. But you can. Oh. So if I take out the tempo and the quant and I hit play, it's going to play immediately when I hit execute. Well, that was boring. Oh, because my tempo clock default is still probably set to like 10. Yeah. Tempo clock dot default dot tempo equals 60 by 120 divided by 60. So again, if nothing is passed in, if I pass in the clock I want now, which is set to 120 BPM, this will be faster. Maybe that got reset somehow. I don't know. Things about. Right? And if I pass in quant 4, clock keeps being reset when I hit. Period, I need to remember that. It started at the next instance of a bar. Cool. I guess I don't know what you mean by define quantization. Essentially, tempo clock's going to return. This is a great question, actually. So let's see if I can figure out how to best do this. So tempo clock, every new instance of tempo clock takes an initial tempo, the time and beats corresponding to the reference time given within the seconds arguments. Seconds, the reference time in seconds, which the beats arguments corresponds, and queue size. So let's see if we can. Let me think about how to pull this apart. If we execute, so this is good. So if I call tempo clock.tempo, it tells us we've got a value of 1. If we multiply that by 60, we would know that that was 60 beats per minute. Tempo clock.beats, whoa. Whenever we execute it, it tells us how many beats have elapsed since our tempo clock began. Beats should, in default, be equivalent to 0. So if it defaults to 0, then beats, we're going to have essentially 1 beat for every click of the clock. Likewise, what was the other one? Seconds. So we can also call seconds and see how many seconds have elapsed. Beats to seconds. Oh. So this is how many seconds have elapsed since our tempo clock started. Same thing, tempo clock dot default dot beats. How many beats have elapsed? They're different because at a couple points in time we made our BPM faster than 60 beats per second, so more beats elapsed than seconds. If we created a new tempo clock, T2 tempo clock, we'll create a new instance of a tempo clock. T2 is a tempo clock. T2 dot tempo times 60 beats per second. T2 dot beats 15. We've had 15 beats. If I execute 1.46. T2 dot seconds. Oh, I guess seconds is always the number of seconds that have elapsed since the program began, which is interesting. Say again. No, so we're getting. And if we call dump, I'm curious to see instance of tempo clock. Cool. Now let's look at. There's a couple other interesting things. So we can set tempo at the number of beats. There's some different ways we can deal with this. Elapsed beats. So those should be cool. So those are the same. Let's see here. T2 dot bar. That's how many bars have elapsed. Tempo clock, we can check if it's running. We have some instance methods. Beat duration. One second. Beats per bar. 4, which is default, does not surprise us. Beat in bar. Elapsed beats. Number of elapsed beats. See, I want to see T2. Oh. So, any other questions on tempo clock? Instances of tempo clock? Great. Cool. Let's move on. Defunk, we'll get there. We ran. Oh, we have not gotten there yet. Oh, okay, great. P key. In many instances, it's useful to reference the values from other keys. To do so, we use the pattern called P key. If we pass in a key from an earlier event variable, we can get its value. So let's look at access a key in an event stream. And there are some things we can do that. So let's see what that means. So we are accessing the freak key. Map the receiver from an assumed exponential input range. Oh yeah, okay. So we're saying the frequency, expected frequency is 400 to 7,000. And we will map the amplitude for lower frequency values closer to 0.05 and higher frequency values inversely to 0.01. Does that make sense? Be quieter as it gets higher. So if we had a frequency of 6615, we had an amplitude of 0.01. When we had a frequency of 431, we had an amplitude of 0.04. So it was louder, lower. Cool. So again, peak key can be useful to pull things out and then essentially as a function, translate that data for later use. Yeah, this is essentially a mapping argument. So again, if we pull it up on simple number, map the receiver from an assumed exponential input range to an exponential output range. So if I had 2, just as an example, exponent, exponent, and we had a range of 1, never 0, to 10, and an output range of 100 to 400, I get back 151. If I get 1, I get back 100. If I put in 10, I get 400. So it essentially, it's just a way of mapping one range of numbers to another range of numbers. In this case, exponential.
Now, you see what,
First, really quick, Bearcat, does that make sense? If I do lin, it essentially takes a linear line from 1 to 10 and another linear line from 100 to 400. So if we pass in, we'll go 1. Makes sense, I get 100, right? Huh? If I pass in a value of 1.5, what do you expect me to get out? Let's be, we'll go 100 to 200. So if I pass in a value of 1.0, I'm saying I've got a range of 1 to 2, and I want that to be a range of 100 to 200. So if I pass in 1.0, I get 100. If I pass in 2.0, I get 200. If I pass in 1.5, I go halfway up that line, I should get 150. We can do this not linearly, but exponentially. And so 1.5 isn't quite 150 because we get that exponential curve. We can also say exponentially to exponentially. Which would map them equally to that. We can talk about that one later. Matthew?
what does,
P key is simply grabbing the value of the dictionary and then allowing us to do something else with it. Yeah. So I could say just as a blank placeholder, P key will pull in amp. I don't know if this will work. Oh, I need a missing comma there. No, I was worried about that. Oh. P. Post line does not work. But notice in here, dir is always getting set to the same as amplitude. So all it's doing is it's saying, give me the value that's stored in the dictionary under the key amp and assign it to the key dir. Something like that, yeah. It's just a way of getting data back and then manipulating that data and passing it back in. Cool. P key must be used after the key reference. Therefore, it matters that our amp key is calculated after our frequency key. Hopefully that makes sense, everybody. If this line was above, I put an amp above frequency, notice we're getting, it's going binary op function. It's kind of freaking out on amp and it doesn't know what to do. So it's just playing the default amp stored in the syntax. It's not pulling anything out of value. So again, that order of operation matters. Okay, prand. Prand chooses randomly from a list. The second argument to prand is the number of times repeat. So again, we'll create a list of prand values, 3 to 5 times, turn it into a stream, 7, 1, 2. Here 5 times, so we got 5 numbers, 7, 1, 2, 2, 2. We did it again, turned it into a stream, executed them, 1, 2, 2, 1, 7. So it's just a way of creating random values. In this example, we're creating a tempo clock with a BPM of 180. And for our MIDI notes, we're saying randomly pass in one of these values, 60, 63, 65, 70. It's a nice jittery thing. In the next example, we're doing something very similar. We're grabbing random values, but we're also offsetting these values by a random octave, up, down, or the same. Created complex bleep flap music. Hooray. White, yeah.
Okay.
So, pseg, actually pull the help up. Pseg defines a function of time as a breakpoint envelope using the same parameters as envelope. These patterns can be used to describe tempo or dynamic variations independent of the rhythmic patterns that express them. So in this case, we're saying we want to have amplitudes go from 0 to 0.3 back to 0 with a segment of 5 seconds and 5 seconds linearly. So this is essentially going to look like a triangle up and a triangle down. And let's listen to what this sounds like. Say again.
Is range part of the system, or is that previously defined?
For this is wrong. This should actually be up under curves, but these are how we do curves. So linear segments. We opened up to go here and we pull it up. So linear right? Exponential. Step. Right? So these values essentially are just defining how we get from one point to another.
But they are built.
They are built into Super Collider. So if we did something like think I don't know if line uses them. Let's see. It doesn't. X line doesn't either. Let's look at envelopes. I'm trying to think of one that would be yes, envelope generator. If we look at on, it has these curve values that we can pass in. And we can do the same thing. So let's say we create a new envelope here.
So you can reference in X, and you know, they want to do
Say that again.
like a curve this way, within, not understood by
It's a
people.
key that is understood. Yeah. So
That's not like
no. So dot dot plot. Right. So we get curve. What were some of the other ones? So let's look at step. So, right, we're seeing the difference between curve and step. If we look at exponential, oh,
that's really control.
so that's exponential. Remember in SuperCollider, if you ever use exponential, can't not pass in 0 because that causes square root of 0 always throws an error in every programming language. Yeah, we can look at some of these. So we got sign. And we can pass them as keys to make you all super happy. So it looks like a sine wave now. And we could, of course, do an array of curves. So we start with a sine, have a Welch on the backside, or have linear and Welch. Squared segments. Cube. Whoa. Just the word step. And we can also pass in our own means. But so that's where this is coming from. So in this case over here, we've got Lin. We've got infinite one, and let's make this more exaggerated. So we'll go up to 7, and we'll do this over 2 seconds and then down over 10 seconds. And if we even added one more 0 here and kept it there for 5 seconds, except we've got a tempo clock of 180, so that's why it's happening so fast. And if we were even slicker with amp, right? So we're able to essentially create stream values that are passed into our Pbinds. It's creating a envelope of amplitude values essentially.
Okay.
Anyone else questions on that? Cool.
There are two,
we're sending it an array of durations. Oh, yeah, we're setting an array of durations. We're saying essentially over the course of a. No. So the first is we're setting an array of amplitude values. So these are the output values for any envelope. It could be amplitude, could be frequency, could be whatever the heck we want it to be. Let's make this simpler, actually. We'll try a different example. Okay, so we're going to set amp to 0.2. Sustain, we're going to keep at 0.1. Duration, we're going to set it 0.5. MIDI note, we're going to set it 60. Let's take a listen. Where is my two patterns? Oh, I'm missing a comma. There we go. Oh, and then our tempo clock is being punk. That's fine. Right now, let's just make our duration even shorter so they're happening quicker. Cool. Right? Everyone comfortable with what's going on here? Really simple. So now we're going to go pseg. In our first list, we're going to go from 60 to 72 to 60 to 60. We've got 4 numbers. These 4 numbers are going to go from 60. I want that to be red. 60 to 72 to 60 to 60, right? Cool. Now, next thing we're going to do is we're going to define how long it takes for that to happen. So let's say pseg. Duration. So let's say it takes 4 seconds, 12 seconds, and then we hang out for 4 seconds. Okay. So again, this is 4 seconds. Whoops, my bad. 4 seconds, 12 seconds, 4 seconds. So it really looks something more like this. Bing, bing, bing. Is that okay so far? Okay. Curve, we're just going to have, we're going to ignore that because it'll default to linear. For repeat, we're going to have it repeat infinitely. So let's take a listen. but we're playing 10 notes per beat. Yeah. Hang out here for 4. Start going back it up. If we change this to something like 3, and then something like 7, it's going to really mess with stuff. The math no longer is cool. Cool. Bearcat, your question. Creating a curve, creating a segment or an envelope segment that then is getting passed through the Pbind. And we're saying at this point in time, yeah, P always stands for pattern. So we've got something like this. And then we could just break it up into time. 1, 2, 3, 1, 2, 4, 1, 2, 3. Whatever, let's assume those are equal. Says, okay, value here is 60, value here is 64, value here is 72, value here is 69.7, 67.2, 64.3, 60, 60, 60, 60, 60. Because that's when the durations are having it happen. If our durations were different, if we pass in some sort of like P and then we got 1, 2, 4, 0.25, repeat for infinite. So it's just grabbing, it's just the two of those things become separated because our math isn't clean. It's just another way of creating algorithmic music. What do you think of that? Me too. P-Funk. So P function, this function optionally is a way to create any kind of pattern using a function. This function optionally takes in the current event as an argument. Therefore, you can access any of the keys in the dictionary declared prior to the instance of P-Funk. For example, below, the P-Funk could not access the position key. In this case, we're calling P-Funk. Notice that our first argument to P-Funk is, of course, a function and a reset function. You're only passing in the function to be used, not a reset function. As we mentioned, that function gets passed the event dictionary as its sole argument. So we're saying if the event dictionary's MIDI note is equal to 77, then the duration will be 1.5. Otherwise, the duration will be 0.15. This is just an if-then statement and supercollider, which I realize we haven't explicitly gone over, but this is what they look like. We can pull it up here. So if, and then two functions, one to execute if true, the second to execute if false.
So keep on telling us
Yep.
keep that function.
Yep.
Why do we use keep?
I was curious about it. Can we rephrase twice? What's happening? Let's stop it. It's passing in a duration of 3. Why is the duration is 0.15? How would you do this with a task? Because we're randomly passing in MIDI notes. So when we get a value of 65, plus we get an octave displacement up, we've got two different random functions going on here. If we pass in the value 77 as a result of those, then we pause for 3 seconds, 3 beats.
So, what's the
875 event is being passed in as an argument. Remember, arg, that's the equivalent to having an argument between 2 pipes.
okay?
Remember, that's why I brought that up a couple of weeks ago, because a lot of times for write function, shorthand is just use 2 pipes on either side. I prefer the keyword arg. So in this case, we're grabbing the MIDI notes key from event. It's not being described as a MIDI note. So let's say some events. So we're going to set it to an environment variable, and then we'll execute this if statement. Okay. I'm just going to stop this for a moment. Gum event. It's a dictionary, right? So we have all of these key value pairs. I can pull out any of these I want to. I can pull out what instrument did we use? Sine tone. What duration was it set for? Whoa. 3. What sustain value did end up being passed in? What was their release value? Event is a dictionary. It could just, it maybe would be easier to have called this event dict. We're just passing in the event dictionary. We can call the argument whatever we want to. When this function gets called, it gets past the event dictionary.
And that's what
Say again. Pfunc gets handed the event dictionary as one of its arguments when it's placed in Pbinds.
So when you substantiate key function, you also
We're passing in, we're taking all of those arguments, which really are stored as a dictionary.
Okay.
And we're passing in that dictionary. You should at some point read about dictionaries probably in SuperCollider, because that would maybe make things more clear.
Sure.
Bearcat. Yeah, no worries. Yeah. Yeah.
But when I look up, okay, when I look up Pbinds in the adult, it doesn't tell me that there's 15 values, there's 15 properties.
It takes in key value pairs. And it applies those key value pairs to the synthdef we've told it to access.
So it's amp is a key value pair. Pbinds is a key value pair.
Amp is a key. Key white produces a value. The two of those together become a key value pair. That's true. I know. What would make you a lot happier is if we use the get sign. Or we used the semicolon. Or we used anything than a whole glut of fucking commas. I don't fucking disagree with you. But the hard part, again, Python is its own clusterfuck. It's a white space language, right? So it's got its own problems. In dictionaries for supercompiler, it's very frustrating, but you can pass in key value pairs separating everything by commas. So it looks like some sort of giant list of nonsense. I do not disagree. Regrettably, that's the way they decided to do it. It's not right. It's not good.
The only way you know what's going on, you have to go to Pbinds.
Let's see here. So it actually looks like maybe we can use an alternate syntax of semicolons. Let's see if that's true. You're not making things difficult. I don't disagree with you. It's literally ugly. Let's see if this works. Does not like it. What if I do star, array, and at the end, do another array. Okay, so that's the alternate syntax. You can pass in a key value array where you prepend the array with a asterisk, and then you can do semicolons. Yeah. Well, that's why certain groups will set rules for how they write code. I mean, many languages have multiple ways of doing it, right? This is not new. I mean, that's whatever. Say again? Yeah, it's pretty the way it was being created.
Out of curiosity, you
if the key MIDI notes in the event dictionary is equal to 77, and we've got two equal signs there.
Yeah, why didn't you?
It's standard in most languages that when we test equivalency, we use two equal signs. If we're testing equivalency as well as type, it's typically three equal signs.
Okay, so we're saying if it's equal to 77, and then the first thing after that is saying that it's 2 and
If it's equal to 77, we set it to 3. If it's false, we pass in this function. Yeah. Cool. All right. But this is important. While patterns can wonderfully encapsulate repetition and musical structure, many patterns need to be updated over time. Unfortunately, Pbind cannot be changed dynamically. Fortunately, there is a corollary to Pbind that can be updated incrementally. Pbind def. I know, incremental event pattern reference definition. So, Pbind def works exactly like Pbind, except it takes one extra argument at the beginning, which is the name of the pattern. Note that Pbind def also creates an event stream player and stores it as one of its internal variables, sometimes called instant variables, but the object return is actually the Pbind def and not the player. Functionally, you can use it just the same as before. Ignore that piece. Well, I actually suggest you probably do. When I work with Pbinds, I pretty much use Pbind def exclusively. Oh. So you can have an algorithmic process that updates Pbind defs, or if you want to get involved with live coding, you can now start to change patterns on the fly. Exactly. New, literally changing the definition of what's being played. Can't do this with a Pbind. Yeah. So let's say this was a Pbind, not a Pbind def. First off, it's going to get angry that it doesn't understand why there's a key value pair sign path to instrument. So we have to release this. And now there's no way to be dot like set. We want there's no W. So there's no way to on the fly update our path. Yeah. Yeah. Playing with someone else or playing with yourself is on the fly. That's creating a name reference on the fly. This is important. And then Pbind clear. It is an important thing to note that a supercollider keeps a global reference of all the patterns playing stop. It's typically a good idea to clear out all references to old Pbind defs if you intend to replay the pattern. In certain scenarios, this can lead to strange behavior if you're not careful, so you can just clear them out. This is a really powerful one, and this is one I want you to really think about spending some time on. Okay, working with audio files and buses. We're almost finished up here on this document. So we can also use audio files and organize them in patterns. This example will use samples from a drum kit. To get started, we first need to get the path of the folder that has the drum kit files. Find a variable called kit folder path. Set the path of the kit folder that came with this code. Okay, so we'll do this. Okay, so this process now executing path directory name pulls in the path where this is stored. We're going to also then copy over kit, sonic programming. It's stored in that kit. We haven't talked about buffers yet. I realize this is something I'd hoped to get to last week, but we went long, so I'm going to save it for next week. I wanted to get the patterns real bad today. So now we can hear. Yeah, so these are files here in Kit, and I'll upload all this to GitHub. So it's just a drum kit. Cool. So we're going to create a simple bass drum. Stop it. Here we put a kick drum pattern together with a snare pattern and sync them using quant. So we've got kick and snare. Kick is set to 1. Snare is rest for 1, play, rest for 1, play. So we're playing on the backbeats. Stop it. So you should do this actually. That'd be kind of cool. Use some of the other things in the buffer. Oh, and then we can start to use reverb. Second drum pattern from above. Then clearly has not finished setting this. That's fine. So bus 0 in bus set to us. So here we can play these and we'll go. We'll have bus as part of it already. Out bus. Let's see here. Bus. So in this case, we're playing a bass and a snare, and they're going through a reverb synth, just like we showed 2 weeks ago, where we started to create buses, create effects, audio effects. I will admit the Freeverb UGen that comes with Super Collider sounds like garbage. And this is where you may want to actually send your audio out to another DAW, depending on what you're trying to do. But if you're trying to do audio processing that Super Collider is good at, keep it internal and then send it out for the final mix or mixing for live performance. Cool. Shit, that's a lot of stuff for today, but it's all on Pbinds. Obviously, your homework for next week is to come up with a sketch that uses patterns of some sort. You are likewise encouraged, if you would want to use some of the comb delay stuff or other processing techniques we looked at over the last 2 weeks after the midterm. We are going to take a 10-minute break, come back at 12:20, and listen to Sam and Fletcher's midterm projects, talk about those. And then we will also launch the final project. Okay? Cool. See you all at 12:20. Huh? Doing okay. Doing okay, yeah. We are both tired dogs, so that's hard. But otherwise, hey, how are you doing? How was when's the interview?
The what now?
When's the interview?
The two.
Cool.
Yeah. And then that's a little bit.
Good. And any problems? Good. I thought that. Oh. Did not see the chat. Sorry, Charlie and Fletcher, for the great questions. I'm so bad when I'm trying to teach up here of also paying attention to the chat. But if either of you want to come by my office hours and talk about the questions you have, happy to keep looking into this. You can really start going pretty far with the algorithmic pattern-based work in SuperPider. And it's not hard to start building up really complex pieces, just as an FYI. All right, here, let me pull up Moodle. Come on, go. Fletcher, just as an FYI, we're going to have you go first. It doesn't seem, unfortunately, as much as Sam asked me the last week to play their piece, I forgot, which is unable to join us today. So I'm sorry for that to Sam. I hope as you watch this on video, Sam, you're able to get some good feedback from all of us.
Sounds good.
You want to tell us anything about your piece, Fletcher?
It is a Shepherd tone generator, and I did a little bit of a yoink and twist with a tutorial.
Good.
You know, saw how to do it, and added more and changed a little bit of numbers, seeing what I could do to it. Ended up breaking it last time,
Good.
but I restarted and did it different, and it works this time.
Good.
So, yeah. It has a bunch of patterns in it.
Yeah, I was just noticing. It's quite apropos to what the heck we've been working on.
Yeah, it's a bit of a pattern thing.
Okay.
And then yeah, just down there, you can play those.
Play these together.
Yeah, you can play yeah. And then the set below that is two going in opposite directions.
comments for Fletcher? Cole says great.
Oh, thank you. I was messing around with it and seeing if it actually like goes forever. And at one point I had it messed up and it would only go for like 10 minutes. But then I think I got it because I left
Oh,
it
they-
on when I went to do errands for like 2 hours.
They should go forever. And this
Yeah.
is where I think Superfighter starts getting really cool when you can put things, set things in motion that will continue forever. And obviously, I think you never intended to play all 7 of these together. I can kind of cheat and figure out how to quickly mix it so they work. But it becomes really cool. And depending on your outlook on life, either like the most meditative, relaxing thing ever, or the stuff of nightmares. Just kind of where you're at, probably. Other comments for Fletcher or questions? Yeah. Bearcat said when some of the lower tones came on, he really imagines himself being able to meditate to something like this.
Yeah, it's pretty nice. That I want to find like the best sounding tones to do. I was trying to do a little make it actually sound good, but it's kind of hard.
I think it sounds great. I think you have to let things be what they are, and it also is going to depend on the space and the speakers, whether they work or not. Honestly, so it is going to be dependent upon a couple of variables outside of just Superfighter.
Yeah, it sounds a lot better on my headphones than my little Bluetooth speaker here.
I would imagine it sounds good. It sounded good in the room here with the sub and the big. Sounded really good. I wish you could have heard it. Great. Other comments or questions for Fletcher?
Yeah, I'm curious what the are those arguments passed in the cloud?
Yes. So what Fletcher's done, so Fletcher Matthew asked, are these arguments being passed into the boundary? And what Fletcher's done is he's defined play shep to be a function with 4 arguments: speed, volume, direction, center, freak, shift. Remember, we can execute functions in SuperCollider with the dot parentheses notation and then pass in corresponding arguments sequentially. So when he does that, we launch this function. It creates a new amp array of 19,200 values that span -5400 to 5399. And each of them gets, it looks like, is getting an exponential value assigned into it. Direction determines if this array goes up or down. And then we take the center frequency shift and offset the array. And then we've got these P monos. And P mono is a monophonic event stream. So a Pbind is a polyphonic. So just for those of you who are comfortable with MIDI and sequencers, if we can play multiple keys on a sequencer, it's a polyphonic MIDI instrument. If when you press one key and then you press another key, it immediately goes to that note and stops playing the other note, that's a monophonic, a single voice synthesizer. So in this case, Fletcher's defined a bunch of monophonic pattern modules, which are essentially serving as monophonic synthesizers. And then we see that he's passing in the key value pair array, which allows us to use our semicolon or our colons, which can be a little bit easier. Duration for, so then we're calling it, we're calling the shep synth def, and shep up here is just sine oscillators that are in stereo, running out left and right, and are multiplied by amplitude. So we call this synth def shep. Duration is set to speed, and speed typically is quite short, by default 0.015 seconds. So we're changing the frequency very frequently. Amplitude gets set to be a sequence of amp array times segments. So we're drawing line segments that go from 0 to 1, 1 to 0. So we're going up and down constantly using a sinusoidal shape and then multiplying that by volume. And then MIDI note that's passed P sequence of MIDI array. So we're playing with the amplitude over time, and we're very quickly changing the note, the value of these synthesizers. And it's set up the same way, but rotated. So essentially starting at different points in the frequency array by fairly substantial amounts. And because we're doing that and we're fading in and out, we get this sense of a shepherd tone. And a shepherd tone is the sense of something that either continually infinitely raises or continually infinitely sinks or decreases. And so when we hear this, we perceive this as always going up higher in pitch. And that's because we're bringing in low frequencies on this nice sinusoidal envelope that are going up in pitch and then eventually fade out and bring in new ones. And because we overlap those, we have the sense of always going up. It's a psychoacoustic principle, shepherd tones. And so he's done that on 14 of them, and then it's just kind of playing around with different parameters in terms of how they start and play. But it's a great example of using patterns to create something we wouldn't expect, because we've been playing around patterns all day today, pretty much assuming that they're doing individual note events with some sort of hard or recognized attack. We're not creating some sort of overlapping mushy thing, which is exactly what's being applied here. Question, Matthew? Fletcher, you had a comment?
Oh no, I was just saying, yeah,
Yeah.
agreeing with the things you're saying.
Ma, ding. Yeah. Yeah. Cool. Cool. Thank you, Fletcher. Congratulations.
Thank you.
Word.
Maybe, or it could be cruel and unusual punishment. I don't know. I don't know. I don't want to say no to you, Bearcat, because obviously I like the inquisitive idea here. Oh, Sam, I forgot. So Sam, we're gonna listen to yours. This will be recorded so you can give feedback later. I forgot that you had the thing where your computer deleted, ate your homework. And I know that was sincere. I know you're a hard student. So thank you for recreating and sharing this with us. So Sam has created a SymphDef here where we've got, it looks like frequency modulation being applied to create a complex waveform. We can get a sense of that. Oh. Lovely. Beautiful. So now we've created a task. So again, very similar to what we could do with Pbinds. We actually could rewrite this code as Pbinds. We've got a task that'll play itself, and then another task that'll play itself. And are these all going to be played together or just one at a time? Okay, one at a time. So let's take a listen. Cool, and it looks like Sam actually wants these all played together. So I'm gonna load these all in and then stop. Oh. Let's load them in for a moment. Beautiful. Okay. And now we have a very specific order. Let's take a listen. Oh, actually, is that right? So we're going to reset all of these so they work. Okay. Yeah, that was great. That was great. All right. Questions, comments for Sam that I can answer on her behalf? Yeah, Matthew. Okay.
Where is the beacon?
It's inherent in the sound. So we've got a percussive envelope with an attack of 1/100th of a second and a release of 3. So we're getting a really sharp attack and then a quick sharp decay and then a very long release. And that gives us a sense of that kind of lingering reverberation. There's no actual reverberation that's being applied to the signal per se.
And what is the dot?
Say again,
What is the dot?
just another type of envelope shape.
Okay.
So remember, envelopes, we can create our own custom shapes with .new, but there's also a bunch of inbuilt shapes, including linen, triangle, sign, percussion, pairs, X, Y, Z, et cetera, et cetera. So it's worth returning to envelope shapes from time to time just to remind yourself what exists there. Other questions or comments for Sam? Yeah. Yeah. So Sam, just to reiterate, Bearcat really liked your piece, enjoyed how it built up over time and then released out of itself. I'd agree. I think it's really nice the way that you structured this piece, kind of this triangle structure in terms of the complexity and then the resolution of it all. Other comments or questions for Sam? Yeah, so what's going on here is, again, set up a synth def. And then we were able to kind of listen to this. And then Sam set up 4 tasks. One thing we don't need that actually gets us in trouble is having this dot play at the end of each task. We can simply assign those to the environment variables that have been specified. And then if we did away actually with these inner parentheses, we could store all 4 of these tasks at once. So for each task, just like a pattern, we're going to see really some similar structures. We've got a task in our task function, and then we passed in inf.do. So this is creating a series of events that are going to occur in order. The first event is we play a synth, the FM synth, with a frequency of 50 MIDI, and a C ratio is doing something with the modulation here. So it's giving us a shimmer, which is really nice. C ratio of 1. And so we play a note, we wait half a beat, we play a note, we wait half a beat, we play a note, we wait half a beat. Dun, 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 and so forth, and then repeat. In the second task, we're doing very similar, but we're an octave up yet. We're an octave up, 12 MIDI notes up. Third task is a much shorter task. These high-pitched little embellishments we had, where there are 4 of them in a row, 5 of them in a row, and then wait 10 beats. And the fourth task, then same thing, just with a little bit different pattern on it, right? So we're able to launch all 4 of these and store them into memory. And then Sam did the genius thing of creating a task to manage the tasks. So we play the bass position for 12 beats. We add in the melody, that octave up thing, and then that plays for 10 beats. So 2 of these are together playing for 10 beats. We add in the high note thing, and that hangs out for 15 beats. Finally, we add in what Sam is calling otherness, and that hangs out with everything together for 39. And then we slowly start to pare this all back until we're left again with only this simple layer, bottom layer, base layer, that we finally stop and pull out. A really clean structure, really nice way to go about procedurally composing a piece. Yeah, great. Cool. Any other questions? Cool. Nice job, Sam. Okay, so we got 2 minutes here. We're not going to get far into it. But the night of December 3rd, which is not horribly far off into the distance. Here, we can look here, actually. We don't need to pull up my messy calendar with all of my shit on it. So 1, 2, you got 3 weeks for a final project. Cool. 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 We're going to perform these final projects in front of someone. Cool. Remember the first day I told you to set December 3rd aside. I need to work with Dr. Costas over in School of Music. In theory, we're going to do something joint together. I've been a horrible collaborator and partner in everything this semester because I'm worthless. So we'll see what happens. Bare minimum, we do something in the production studio and it'll be lovely. What I'd like, Thanksgiving is the 25th. So so essentially, I know this is not a lot of time. I meant to actually open this last week, but then wasn't paying attention. So you can do whatever you want. You can do whatever you want. Super Collider needs to be involved significantly. At one point in time, I said this work needs to be made exclusively within Super Collider. I don't know that I'm going to stick with that requirement. I want you to really do what makes the most sense to you, but I would like Super Collider to be a significant element of that final project. And if you had it in you, ideally, Super Collider would be the entirety of the environment. But you don't have to, okay? We'll take that out. It should be a significant work. It can either be a performance-based type work or it can be a gallery-based type work. As an example, Fletcher's Shepherd Tones would be something we probably wouldn't put on a concert. We might actually, and there'd be ways to do that that'd be cool. But those could instead exist as a piece that I put in a room somewhere and they just played for the duration of the night. And people could go in there, lay down on the floor, whatever they want to do. Or you can have a discrete piece that is X minutes long. Next week, you got to come with a sketch for your piece. So we're not going to have you do, you got to do a pattern sketch next week, and you got to come with a final project proposal and sketch for that as well. So you got 2 things due next week. Cool? Wow. No. Patterns are just, I just want you to play around with patterns. But your final project, you also need to start thinking about a sketch and what you're going to do for that. We will jump into a lot more detail in the final project next week, but you know I really like openness in how we approach things in this class. The 400 level class, you're totally open to do whatever you want to do. I have office hours from noon to 1 on Monday. I will make time for each of you in this class. I will make a lot of time for each of you in this class. If anyone wants to get together and work on problems, talk through things, look at specific techniques we haven't gone over this semester, shoot me an email. I will give you time. I really want you to feel like you've gotten a good piece out of this experience. So, and I want to make sure that we recognize the beginning of the semester got off to a little bit of a weird hitch. I really care about all of you. You're all doing great work, and I want to give everyone plenty of time, okay? So if you want time, send me an email. Come to my office hours or set stuff up on calendar. Questions? Yeah, because here's how the calendar works out, unfortunately. Next Friday, you'll give me a basic idea. The next time we meet is the Friday of the performance. No, I'm not kidding. The Friday after that, we'll then do a recap of the entire semester. Thanksgiving always messes things up.
Do you have a final after that?
No, we will not meet during final. We will do a recap in here. What you will do is I will record everyone's performances the night of the 3rd. I will give you that, and then I'll expect you to turn that around into a documentation of your piece that you could put up on a website or other things. We will listen to each of those in class on Friday and have a critique essentially of the performances from the week previous. So the final Friday, the 10th or whatever that is, will be a final critique of our final projects.
Next time we have to come to one idea and work on it by ourselves.
I mean, you probably should be working this next week on your final project. And if you're not sure if it's going to work, I encourage you to come talk with me sooner than later. If you got ideas now you want to bounce around, I'm happy to go up to my office and hang out for a few minutes. We can powwow, or we can meet in there and roundtable some discussions and some ideas. If you want to get me next week, welcome to do that. I'll hang out for about 20, 30 minutes though before I head home. If anyone wants to do some bouncing around of ideas, this is a quick turnaround. Well, I know it's a quick turnaround. I'm sorry. This semester is a clusterfuck. I know it's a clusterfuck. I'm sorry, but you're all awesome. It's going to be a great final project. I'm not worried in the slightest. I will help you get through it. The last thing is, think about live performance possibilities. Think about live performance possibilities. It can be a fixed work, totally fine. Totally fine. But think about live performance possibilities. For those of you who are really into visuals and film, think about fixed film pieces that you could do something with Super Collider too. It can go anywhere. We're open to anything. Cool?
Dr. Music,
Yes, sir.
are the performances limited to that room, or is there a possibility to go do like the production space or something?
What do you mean?
I mean, if it was an audio-visual performance or an audio-visual piece, could it be displayed in the production lab on a wall or something? Or are we trying
Yeah,
to?
like if it's a gallery style piece.
Yeah.
Yeah, I'll make sure if people are doing gallery style pieces, I will figure out how to have them near or in the same space for extended periods of time for people to experience.
Okay, cool. Thanks.
So everything is open. That's the key story. Everything is open. We're just going to present them somehow Friday the 3rd, and we'll figure out what that means next week. Cool. And the last thing that we'll go over for topics next week is audio buffers and how to use actual audio files, since clearly that might come in handy. Have a great day, everybody.
Thank you.
Yeah, see you, Fletcher. See you, Charlie.